Right now, without feeling a thing, you are moving through space faster than almost anything humans have ever created. Earth is spinning at over 1,000 miles an hour, but that's only the first layer of motion. At the same time, we orbit the Sun at 67,000 miles an hour, racing around our star in a silent loop that has repeated for billions of years. But even this incredible speed is just a small part of a much bigger journey. The Sun itself is dragging us through the galaxy at over 400,000 miles an hour, carrying our entire solar system in a vast orbit around the Milky Way's center. Every second, we cross more than 100 miles of empty space without ever sensing the motion. If you could pull back and watch our solar system from a fixed point outside the galaxy, you wouldn't see a calm, circular orbit. You'd see a curved, spiraling path through an ocean of stars, a journey that takes 230 million years to complete. That period is called a galactic year. Since the Earth formed 4.5 billion years ago, we've made only about 20 laps around the galaxy. The last time our part of the solar system was in this same position in the Milky Way, dinosaurs did not exist, mammals had not evolved, and the continents were unrecognizable. Every geological era you can imagine unfolded during a single orbit around the galactic center. As we move on this enormous path, the solar system doesn't glide smoothly. It bobs up and down through the Milky Way's disk like a boat riding long, slow waves. Every 33 million years, we pass through the densest part of the galactic plane, then drift upward, then fall back down again. Some scientists believe these crossings might influence life on Earth by exposing our planet to increased cosmic radiation, shifting asteroid patterns, or disturbing distant comets. Our position in the galaxy is not just a backdrop. It may affect the history of life itself. Right now, we're traveling through one of the quieter regions of the Milky Way, and our location might be one of the reasons life had the chance to flourish on Earth. Surrounding us is a vast cavity of hot, thin gas called the local bubble. This bubble extends for more than 1,000 light years in every direction, and our sun drifts inside it like a speck of dust inside a hollowed-out cavern. But this cavern wasn't carved by gentle processes. Millions of years ago, multiple massive stars exploded in violent supernovas, each one releasing more energy in seconds than our sun will produce in its entire 10 billion year lifetime. Those explosions swept away gas and dust, clearing out this enormous empty region and creating the bubble we live in. The walls of the bubble aren't truly empty. They're made of hot, X-ray emitting gas heated by those ancient blasts. If you could see in high-energy light, you'd see a glowing shell surrounding our solar system on all sides. The atmosphere of Earth and the protective environment of the heliosphere shield us from most of that radiation. But the local bubble itself acts like a partial buffer, keeping dense clouds and harmful cosmic conditions farther away than they would otherwise be. In a way, our civilization exists inside the aftershock of long-dead stars, an environment that once would have been deadly, but now provides a rare pocket of relative calm. Our solar system isn't centered inside this bubble. It's drifting toward its edge, heading into regions where the gas grows denser and colder. In a few million years, we'll exit the bubble entirely and enter a new galactic neighborhood with different radiation levels and cosmic conditions. But for now, as we speed silently through space, we remain in this protective cavity carved out by ancient explosions. But just beyond this calm region, star formation is unfolding in some of the most beautiful and violent ways imaginable. Only a few hundred light years away, lies a place where the darkness is alive with collapsing gas clouds, newborn stars, and colossal pillars of dust illuminated by blazing starlight. This is the Orion Molecular Cloud Complex, the closest major star-forming region to Earth. If human eyes could see infrared light, the Orion region would dominate our night sky with glowing arcs and bright knots of newborn stars. Inside the Orion clouds, gravity is constantly pulling vast regions of gas inward. As the material collapses, it heats up, and when the temperature at the core becomes high enough, nuclear fusion ignites and a new star bursts into life. These newborn stars are not gentle neighbors. They unleash fierce stellar winds, streams of particles racing outward at hundreds of miles per second. These winds carve out cavities and tunnels in the surrounding gas, shaping the clouds into cliffs, towers, and arches. Some regions glow brightly from the intense ultraviolet light of massive young stars, transforming the dark molecular clouds into luminous nebulas. Not every clump of gas becomes a star. Some collapse partially into failed stars called brown dwarfs, objects too small to ignite full fusion. Others get torn apart by the violent activity of their more massive companions. But wherever stars do form, they form together. Dozens or hundreds of them emerge from the same collapsing cloud, creating clusters of stellar siblings that begin life in close proximity before drifting apart over millions of years. Our own Sun was born in such a cluster about 4.5 billion years ago. Its siblings are now scattered across the Milky Way, separated by unimaginable distances impossible to identify. Everything we see in these star-forming regions is part of a continuous cycle. Massive stars are born, burn brilliantly, explode, and scatter heavy elements back into the galaxy. Those elements, carbon, oxygen, iron, calcium, become part of new clouds, new solar systems, new planets, and eventually new forms of life. Every atom in your body except hydrogen and helium was forged inside a star that lived and died long before the Earth existed. As we leave the quiet bubble around our solar system and move deeper toward the crowded regions of our galaxy, the structures grow larger, the forces stronger, and the events more dramatic. Ahead of us lie the spiral arms of the Milky Way, the great star factories of our cosmic home, and the path toward the galactic center, where the most extreme environments of all await. As we move outward from the familiar regions around our Sun, we enter a structure that defines our true place in the Milky Way. Our solar system doesn't drift through the galaxy at random. It sits inside a vast lane of stars, gas, and dust known as the Orion Arm, our galactic neighborhood, stretching thousands of light years in both directions. For a long time, astronomers thought this arm was just a tiny spur, a minor branch between the Milky Way's major arms. But modern observations revealed something surprising. The Orion Arm is far more substantial than anyone expected, a significant structure woven into the architecture of the galaxy. To visualize the galaxy, imagine looking down at a giant spinning hurricane made of stars. The bright spiral arms you see are not solid structures, but regions where stars and gas bunch up due to gravitational patterns called density waves. These waves are like slow-moving traffic jams. As stars and gas orbit the galactic center, they pass in and out of these high-density regions, creating the appearance of spiral arms that wrap gracefully around the galaxy's core. The arms don't rotate like a rigid wheel. Instead, they maintain their shape because of the way matter flows through them, gathering, compressing, and then dispersing. It's this compression, similar to squeezing a cloud, that triggers the birth of new stars. Every time a gas cloud enters a spiral arm, the increased density squeezes it tighter. Gravity takes over, pulling the cloud into smaller pockets that eventually collapse to form stars. Massive stars, burning intensely hot and bright, carve out cavities in the surrounding gas with their fierce radiation. These same giants live fast and die violently, exploding as supernovas that enrich the surrounding space with heavy elements. This constant cycle of compression, birth, and destruction is what keeps the Orion Arm alive and glowing. Our solar system drifts about halfway between the galaxy's center and its outer edge, a region astronomers call the Galactic Habitable Zone. Closer to the core, radiation levels soar, supernova rates increase, and gravitational chaos becomes too great for stable planetary systems. Farther out, the density of heavy elements drops, making it harder for rocky planets like Earth to form. By cosmic luck, we occupy a sweet spot, far enough from the core to be safe, yet close enough to star-forming regions to have the ingredients necessary for life. Our location isn't just comfortable. It may be one of the rare places in the galaxy where a planet like Earth could develop and sustain complex organisms. Within this arm, stars are born not singly, but in clusters. When a massive molecular cloud collapses, it fragments into dozens or hundreds of star-forming cores. These stellar siblings begin life crammed together, sharing the same birthplace. Over millions of years, gravitational nudges from other stars and the galaxy's rotation slowly tear these clusters apart. The siblings drift away from each other until they scatter across the Milky Way, becoming lone travelers. Our own sun was born in such a cluster around 4.6 billion years ago, surrounded by thousands of siblings that are now lost somewhere among the hundreds of billions of stars in the galaxy. Somewhere out there, far beyond our ability to trace, are the long-dispersed brothers and sisters of our sun. Not all stars in the Orion Arm shine with youthful energy. Mixed among the brilliant newborns are the remains of stars that died long ago. One of the most common remnants is the white dwarf, a dense, Earth-sized core left behind when a star like our sun exhausts its fuel. A single teaspoon of white dwarf material would weigh as much as a car. These stellar remnants glow faintly for billions of years, cooling slowly as they fade into darkness. Some white dwarfs pull gas from companion stars, building up enough material to trigger explosive outbursts called novas that briefly make them shine tens of thousands of times brighter. Even stranger are neutron stars, the ultra-dense remnants of massive stars that exploded as supernovas. Imagine something more massive than our sun crushed into a sphere about 12 miles across. A sugar cube-sized chunk of neutron star material would outweigh Mount Everest. Some neutron stars spin rapidly while emitting beams of radiation that sweeps across the sky like cosmic lighthouses. When these beams pass across Earth, we detect them as perfectly timed pulses, pulsars with the precision of atomic clocks. The fastest ones spin hundreds of times per second. Their magnetic fields are so powerful that if one were placed where our moon is, it would wipe every magnetic strip and electronic storage device on Earth. These stellar corpses remind us that our spiral arm is not just a cradle of star birth, but also a graveyard filled with remnants of stars that lived and died over billions of years. Their explosions and stellar winds fill the Orion Arm with heavy elements that become the building blocks of planets, moons, and eventually life itself. The Orion Arm is more than just our home. It's a crossroads where star formation, stellar evolution, and galactic dynamics all interact. The stars we see in our night sky, including familiar constellations like Orion, Cygnus, and Perseus, are all part of this same spiral structure. When you look up on a clear night, you're seeing only a tiny slice of the arm we inhabit. But the Orion Arm is only one small branch of the Milky Way's sprawling architecture. Beyond it lie the massive primary arms, regions filled with far more intense star formation and much more powerful cosmic forces. As we move outward from our calmer local neighborhood, we begin to encounter areas where stars are larger, brighter, and more violent than anything we see around us. Some of these massive stars burn 50 or 100 times brighter than our sun, living short, furious lives before exploding with spectacular force. Ahead of us lies one of the Milky Way's main highways of star formation, the Perseus Arm. This massive structure stretches tens of thousands of light years, filled with some of the galaxy's most energetic and luminous stars. Compared to the Orion Arm, the Perseus Arm is a cosmic metropolis, crowded with stellar giants and immense star-forming clouds. As we leave the relative calm of our familiar galactic home, we prepare to enter regions where imagination struggles to keep up with reality. Regions shaped by explosions, gravity, radiation, and the birth and death of stars on a scale far beyond anything found near our sun. As we drift farther from the quiet comfort of the Orion Arm, the Milky Way begins to reveal structures far larger, brighter, and more turbulent than anything in our local neighborhood. The first of these giants is the Perseus Arm, a major spiral arm of the galaxy, stretching tens of thousands of light years and glowing with the light of countless massive stars. Moving into this region is like traveling from a calm countryside into a vast, crowded metropolis, where everything is louder, hotter, and far more energetic. The Perseus Arm is home to some of the largest and most luminous stars in our galaxy. These massive blue-white giants can weigh 50 or even 100 times more than our sun. Their intense radiation floods the surrounding space, lighting up colossal clouds of gas and dust like cosmic lanterns. Star formation here is relentless. Dense molecular clouds collapse under gravity to form new stars, and the most massive among them quickly ignite, carving out glowing cavities with their fierce winds. Some of the Milky Way's most iconic star-forming regions, like the towering structures carved inside the Eagle Nebula or the bright glowing petals of the Rosette Nebula, owe their beauty to these stellar behemoths. But these giants live brief, dramatic lives. After only a few million years, they reach the end of their fuel and explode as supernovas with an energy output that outshines entire galaxies. Each explosion sends shock waves racing through the surrounding gas, triggering the formation of even more stars in a continuing cycle of creation and destruction. Traveling through the Perseus Arm would feel like witnessing an entire cosmic ecosystem at work. The constant birth of new suns, the violent deaths of massive stars, and the shaping of matter into dazzling nebulas that glow across thousands of light years. Yet the Perseus Arm is only one of the extraordinary structures we encounter on this journey. Scattered throughout the galaxy are enormous cities of stars, clusters so densely packed that they strain the imagination. The oldest and largest of these cosmic cities are globular clusters. These ancient spherical swarms contain hundreds of thousands to millions of stars, all crammed into a region only a few hundred light years across. If Earth orbited a star within the center of a globular cluster, night would never truly fall. Thousands of stars brighter than Venus would shine overhead, turning the sky into a permanent field of brilliant light. In our part of the galaxy, the nearest star is more than 4 light years away. In a globular cluster, the distance between stars can shrink to the size of our solar system. Gravity rules everything here. Planetary systems struggle to survive. Stars constantly tug on one another, redirecting orbits and flinging unlucky companions into interstellar space. These clusters have existed since the early universe, surviving the birth and evolution of galaxies that have formed, merged, and reshaped themselves over billions of years. Closer to the galactic disk are open clusters, much younger, looser gatherings of stars formed from the same collapsing gas cloud. These clusters are cosmic nurseries in progress. The Pleiades, or Seven Sisters, is one of the most famous open clusters visible to the naked eye. It contains more than 1,000 stars born within the last 100 million years. Many open clusters still sit inside the remains of the molecular clouds that created them, allowing us to witness star formation in real time. These clusters are temporary structures. Over hundreds of millions of years, gravitational interactions gradually scatter their members until they dissolve completely, leaving their stars to wander the galaxy as individuals. But the spaces between these star cities are not empty. Flowing through the galaxy is an invisible network of interstellar rivers, vast streams of gas and dust shaped by gravity, stellar winds, supernovas, and the rotation of the Milky Way. These rivers carry the raw material for star formation across thousands of light years, feeding the major spiral arms and igniting new bursts of creation. Some flows spiral inward toward the center of the galaxy, supplying gas to the massive clouds that dominate the inner regions. Other flows stream outward, distributing heavy elements forged in previous generations of stars to the galaxy's outskirts. These interstellar rivers are turbulent and chaotic. Supernova shock waves, radiation from massive stars, and magnetic fields create swirling eddies, cold pockets, and hot, thin regions heated to millions of degrees. In some places, gas collapses into dense molecular clouds that become stellar nurseries. In others, the same forces tear clouds apart before they can form stars. The result is a galaxy-wide circulation system that continuously mixes matter, redistributing the building blocks of planets and life. Magnetic fields add another layer of complexity. Though incredibly weak compared to anything we can feel on Earth, galactic magnetic fields stretch across thousands of light years. They guide the flow of charged particles, shape gas clouds, and influence how stars form. Cosmic rays, high-energy particles traveling near the speed of light, race along these fields like bullets moving through invisible pipes. As we follow these gas streams deeper into the galaxy, the environment becomes progressively more crowded and energetic. The pressure rises, the density increases, radiation intensifies. The scale of star-forming activity grows far beyond what we see near the Orion Arm. We are entering the galaxy's inner regions, where star birth rates soar and gravity molds matter into ever larger, more complex structures. Ahead lies one of the Milky Way's grandest features, the Scutum Centaurus Arm. This massive spiral arm stretches more than halfway around the entire galaxy, forming a colossal arc of stars and star-forming regions. It is one of the most active stellar production zones in the Milky Way, powered by rivers of gas funneled inward from the galaxy's outer regions. In this arm, stars form at rates thousands of times higher than in our quiet neighborhood. Red supergiants glow like colossal embers. Blue hypergiants blaze with the intensity of millions of suns. Stellar clusters collide. Gas clouds collapse on massive scales. Compared to this inner superhighway of star formation, the Orion Arm is a calm, quiet suburb. The Perseus Arm is a vibrant city, but the Scutum Centaurus Arm is a sprawling industrial heartland, where the combined forces of gravity, magnetic fields, and galactic rotation drive the most powerful star-forming engine of the Milky Way. Our journey is about to enter this colossal structure, and from here onward, every step takes us closer to the most extreme and mysterious regions of our galaxy. the turbulent zones that feed the central bar, the massive molecular clouds near the core, and ultimately, the dark, violent heart of the Milky Way itself. As we continue our journey deeper into the Milky Way, the calm, familiar structures of our local neighborhood fall away, and the galaxy begins to reveal one of its greatest giants. The Scutum Centaurus Arm rises ahead of us like a vast cosmic highway, stretching more than halfway around the Milky Way. This is the galaxy's longest and most massive spiral arm, an immense arc where star formation erupts on scales far beyond anything found in the Orion or Perseus arms. Entering this region is like stepping into the core of a stellar factory that has been running uninterrupted for billions of years. Here, the density of matter increases dramatically. Thick rivers of gas are compressed by the arm's gravitational structure, igniting continuous chains of star formation. Some of the most luminous giants in the Milky Way are born here. Blue-white stars so massive and hot they shine with millions of times the brightness of our sun. These stars burn through their fuel rapidly, living brief lives before exploding as supernovas that can be seen from other galaxies millions of light years away. Their radiation sculpts enormous cavities in the surrounding gas, carving bubbles and tunnels that stretch for dozens of light years. The Scutum Centaurus Arm is not just a birthplace for stars, it is a launchpad. The chaotic gravitational environment regularly flings stars outward at extraordinary velocities. These runaway stars can travel so fast that they eventually escape the Milky Way entirely, becoming lonely wanderers drifting in intergalactic space. Many of these exiles began their lives in dense star clusters formed within this arm. Their ejection is caused by close encounters with massive stars or interactions with supernova shockwaves. Some are pushed to speeds exceeding 1,000 miles per second, becoming some of the fastest moving stars in the galaxy. The star clusters in this region are exceptionally dense. Some are so tightly packed that thousands of stars occupy a space only a few light years across. In these clusters, gravity creates a constant tug-of-war, pulling stars into new paths, disrupting planetary systems, and shaping the evolution of entire stellar populations. Many clusters contain red supergiants so enormous they would engulf the orbit of Mars if placed where our Sun is. Others host blue hypergiants that burn with incredible intensity, producing winds powerful enough to strip gas from neighboring stars. As we travel through this massive spiral arm, the galaxy begins to transition once again. The Scutum Centaurus Arm gradually funnels inward toward a colossal structure hidden near the Milky Way's heart. This is the Galactic Bar, a vast, elongated formation of stars and gas stretching more than 27,000 light-years from end to end. For billions of years, this bar has acted as a gravitational engine, shaping the structure of the Milky Way and controlling the flow of matter throughout its disk. Unlike the spiral arms, the galactic bar rotates as a single unit, sweeping around the center of the galaxy and dragging gas along with it. As gas clouds orbit the Milky Way, they encounter the gravitational influence of the bar. Instead of moving in smooth, circular paths, the clouds are channeled into elongated orbits that spiral inward. The bar effectively acts like a cosmic pump, drawing gas from the outer galaxy and funneling it toward the center. Without this structure, the inner regions of the Milky Way would be far quieter, with fewer stars forming and far less activity near the core. This gravitational engine is not uniform. Along its length are dense lanes of gas and dust, twisted around the bar like threads wrapped around a gigantic spindle. These bar spirals are some of the most active star-forming regions in the galaxy, powered by the constant inflow of fresh material. The environment becomes increasingly chaotic the closer we move toward the bar's center. Stars crowd together, gas clouds collide, and gravitational forces intensify. The bar's rotation helps maintain the spiral pattern of the Milky Way. If it spun too fast or too slowly, the galaxy's spiral arms would either wind up tightly or unravel completely. Instead, the bar's delicate motion stabilizes the galaxy's shape, allowing billions of stars to orbit peacefully over cosmic timescales. But its most important role is directing material toward the central regions, feeding the enormous molecular clouds near the core. As we follow these gravitational channels inward, the environment grows darker and more turbulent. We enter a region where the gas clouds become immense, bigger than any previously encountered. One of the most massive is Sagittarius B2, a molecular cloud so large it contains enough raw material to create 3 million stars like our Sun. Even if you compressed our entire solar system into the size of a marble, Sagittarius B2 would still be larger than a stadium. Its interior is incredibly cold, just a few degrees above absolute zero, allowing complex molecules to form and survive. Inside this giant cloud, chemistry unfolds on a staggering scale. Astronomers have detected more than 150 types of molecules here, including organic compounds that serve as building blocks for more complex structures. Ethyl alcohol, the kind found in beverages on Earth, floats freely inside this cloud in quantities millions of times greater than all the oceans on our planet combined. Other regions contain molecules that produce scents similar to raspberries or flavors reminiscent of rum. Radiation from nearby stars, shock waves from supernovas, and magnetic fields constantly stir the cloud, creating a chaotic internal landscape of waves, eddies, and dense pockets ready to collapse into new stars. These massive molecular clouds near the galactic center are not calm nurseries. They are storm zones. Gravity fights against intense magnetic fields and turbulent motion, preventing many clouds from collapsing into stars. As we move closer, the environment transforms into something even more extreme, the central molecular zone. This region spans about 1,000 light-years and contains more gas and dust than the rest of the inner galaxy combined. Temperatures swing wildly between freezing cold cloud cores and superheated plasma millions of degrees hot. Star formation in this region behaves differently from anywhere else in the Milky Way. Although the central molecular zone contains enough material to create millions of new stars, its actual star formation rate is unusually low. Something is resisting collapse, likely the powerful magnetic fields threading through the region, heated by the supermassive black hole and the thousands of massive stars that populate these inner zones. The deeper we travel, the darker the environment becomes. Dense clouds block visible light completely, leaving only infrared and radio signals to reveal what lies ahead. The gravitational forces increase, the density of matter rises, and the chaotic interplay of gas, stars, and magnetic fields reaches a level unmatched anywhere else in the galaxy. Ahead, hidden behind a veil of dust and turbulent energy, lie the shadowed regions surrounding the galactic center, home to some of the strangest and most violent phenomena in the Milky Way. As we enter the innermost regions of the Milky Way, the galaxy transforms into something unrecognizable. The calm structures of the outer arms give way to a chaotic arena where gravity, radiation, and magnetic fields collide with overwhelming force. This region, called the Central Molecular Zone, stretches roughly 1,000 light-years across and contains as much gas and dust as the rest of the inner galaxy combined. Yet here, where the density of raw material should create an explosion of starbirth, something strange is happening. Star formation is heavily suppressed. Massive clouds that have more than enough mass to collapse into stars remain suspended in a delicate, restless balance. The reason lies in the extreme environment. Magnetic fields in the central molecular zone are thousands of times stronger than anything in our local region. These fields thread through the clouds like invisible steel cables, resisting the pull of gravity and keeping them from collapsing. Between the clouds is hot plasma, heated to millions of degrees by supernova shockwaves and energy from the galactic center. The scene is a cosmic contradiction. Regions as cold as 10 degrees above absolute zero, floating beside pockets of searing gas so hot it strips electrons from atoms. Our only view into this darkness comes through radio waves. Dust blocks visible light completely, but radio telescopes detect a constant stream of signals from the galactic center. These signals rise and fall in intensity, sometimes flaring by hundreds of times within minutes. Each flare marks a moment when gas falls inward and heats up before vanishing forever into the central black hole. The region is full of mysterious threads called non-thermal filaments, long, thin structures that glow only in radio wavelengths. These filaments stretch for hundreds of light years, illuminated by electrons spiraling along powerful magnetic fields. Their origin remains one of astronomy's most puzzling mysteries. Radio observations also reveal gas clouds being torn apart by gravity. One such cloud, named G2, was seen stretching like taffy as it swung close to the central black hole. Over several years, astronomers watched its destruction in real time as its material was pulled into a long filament and heated to extreme temperatures. Near these shredded clouds, hot ionized gas streams inward along curved arcs, tracing complex orbits around the galactic center. Some streams loop around the black hole several times before finally crossing the point of no return. Moving deeper, the darkness gives way to one of the most crowded regions in the known universe, the nuclear star cluster. Packed into a space smaller than the distance between our sun and the nearest star, more than 25 million stars orbit the galactic center. If Earth were located here, our sky would never experience night. Thousands of stars brighter than the full moon would shine continuously, covering the darkness with a brilliant, shimmering glow. The density here defies comprehension. Stars are separated by distances smaller than the size of the solar system. In the very center, some may pass close enough that their outer layers interact. Gravity dominates all. Planetary systems cannot survive in this environment. Any planets would be flung away or torn apart within thousands of years. Many of the stars in this cluster are extreme. Wolf-Rayet stars burn so hot they blast off their outer layers with powerful winds. Red supergiants swell to sizes larger than Earth's orbit. Blue hypergiants shine with the luminosity of millions of suns. Their life cycles are accelerated by the intense environment, forming, burning, and exploding within a few million years. Among these stars are compact remnants, white dwarfs, neutron stars, and stellar mass black holes. When these objects pass close to one another, they can spiral together and merge, releasing bursts of gravitational waves that ripple across the galaxy. Some stars are accelerated to incredible speeds through gravitational slingshots, becoming hypervelocity stars that race out of the cluster at more than 1,000 miles per second. These stellar refugees have been found moving through the edges of the Milky Way, each one an exile from the chaos of the galactic center. At the heart of all this motion lies the most massive and mysterious object in the galaxy, Sagittarius, a star, the supermassive black hole. Containing the mass of 4 million suns compressed into a region smaller than Mercury's orbit, it anchors the orbits of everything around it. For decades, its existence was suspected but unproven. That changed when astronomers began tracking individual stars near the center, using infrared telescopes capable of seeing through the dust. One star, named S2, became the key to confirming the black hole's presence. S2 follows a wildly elongated orbit, taking 16 years to complete one loop. At its closest approach, it speeds past the black hole at over 25 million miles per hour. Its motion is so extreme that it exhibits clear signs of general relativity. Its orbit precesses, and time runs slower for it compared to stars farther away. Only a supermassive black hole could cause such an orbit. Despite its fearsome mass, Sagittarius A star is relatively quiet, feeding on only small amounts of gas. But when material does fall inward, it produces bright flares that briefly outshine all the stars in the cluster. The gas spiraling toward the event horizon heats to billions of degrees and emits X-rays and radio waves before disappearing forever. The event horizon itself is not a surface, but a boundary, a region where escape velocity exceeds the speed of light. Anything crossing it is lost to the universe. Approaching the event horizon is a journey into distorted space and warped time. To a distant observer, anything falling toward the black hole appears to slow down, fade, and freeze at the edge of the horizon. But to the falling object, time continues normally, with no visible boundary marking the fatal transition. Closer still, tidal forces stretch matter apart in a process known as spaghettification, pulling more strongly on the nearest point and tearing objects into long, thin strands of particles. Even here, nothing escapes the black hole, but the regions just outside the horizon produce powerful relativistic jets. These narrow beams of particles are launched by twisted magnetic fields in the spinning disk of superheated gas. The jets from Sagittarius A star are faint compared to those in more active galaxies, but they still accelerate particles to nearly the speed of light. When these particles collide with surrounding matter, they generate gamma rays that travel across the galaxy. Now, having reached the very heart of the Milky Way and stared into the darkest object within thousands of light years, we begin to pull back. The dense star cluster fades, the radio filaments thin, the torn gas clouds grow distant, and the monstrous gravity of Sagittarius H becomes only one component of a much larger cosmic architecture, the vast, interconnected system that surrounds our galaxy's core and shapes everything far beyond it. As we rise from the galactic center and drift outward, the stars begin to thin and the chaos softens, revealing something hidden beneath the Milky Way's luminous disk. Surrounding our galaxy is an enormous invisible sphere called the dark matter halo. It cannot be seen, touched, or detected by ordinary light, yet it outweighs everything we can see by roughly 10 to 1. This halo stretches hundreds of thousands of light years beyond the visible galaxy, encompassing not only our spiral arms, but also many of the smaller galaxies that orbit us. Without this invisible scaffolding, the Milky Way as we know it could not exist. The stars in the outer regions would fly off into space, unable to remain bound by the gravity of visible matter alone. Instead, the halo's unseen mass provides the gravitational glue that holds our galaxy together. The Milky Way does not exist in isolation. Dozens of satellite galaxies orbit it, like small moons around a giant planet. The most famous are the Large and Small Magellanic Clouds, visible from the southern hemisphere as glowing patches of light. These galaxies contain billions of stars and are connected to us by long rivers of gas called tidal streams. Over billions of years, the Milky Way has been stealing stars and gas from these companions. Some smaller satellites have already been consumed entirely, their remnants stretched into faint stellar trails that wrap around our galaxy. Others, like the Sagittarius dwarf galaxy, are currently being torn apart in slow motion, their stars pulled into looping arcs that will eventually merge with the Milky Way's outer regions. This process, galactic cannibalism, has shaped our galaxy's history. The Milky Way has grown not by remaining alone, but by devouring smaller galaxies and absorbing their matter into its structure. In time, even the Magellanic Clouds will be stretched thin and assimilated. But all of this pales compared to the cosmic event that awaits us in the far future. Andromeda, the nearest large spiral galaxy, is racing toward the Milky Way at about 250,000 miles per hour. In roughly 4.5 billion years, the two galaxies will collide. Despite the dramatic name, few stars will physically collide. The distances are too vast. Instead, the galaxy's gravitational fields will merge and distort one another, sending stars into new orbits and flinging some into intergalactic space. Enormous tidal tails will stretch across hundreds of thousands of light years as both galaxies pass through each other again and again. Each encounter will reshape them further until they finally merge into one massive elliptical galaxy. Astronomers have already given this future structure a name: Milkomeda. Inside Milkomeda, the supermassive black holes from the Milky Way and Andromeda will spiral together, sending gravitational waves across the universe before merging into an even larger black hole. Our solar system may survive the merger, although its position in the new galaxy will almost certainly change. It might be flung into the outskirts or drawn closer toward the new center. But Earth itself will be uninhabitable long before then, transformed by the sun's evolution into a red giant. After the merger, star formation will continue for some time, but eventually the supply of cold gas will run out. Supernovas and stellar winds will have blown much of the gas away, while the rest becomes too warm and diffuse to collapse. Gradually, the galaxy will enter a stage astronomers call red and dead, populated mostly by aging red stars with few new ones forming. Over billions more years, the bright blue giants will vanish. Medium-sized stars like the Sun will become white dwarfs, and the galaxy will grow ever dimmer. On far longer timescales, even the faint light of red dwarfs will fade. The universe itself will continue expanding, driven by dark energy, pulling galaxies farther apart until only the closest gravitational structures remain bound. Over trillions of years, stars will burn out completely, leaving black dwarfs, neutron stars, and black holes scattered across an increasingly dark cosmos. Eventually, even black holes will evaporate through Hawking radiation, releasing their remaining energy into space over timescales so vast they are almost impossible to imagine. Long after the last star has died and the final black hole has vanished, only a thin sea of cold particles and stretched-out radiation will remain. The Milky Way's story, like that of every galaxy, will end quietly in the deep future. But before that distant fate arrives, it's worth remembering that our galaxy, enormous as it is just one among many. Some galaxies are far larger and more powerful. Elliptical giants like IC1101 stretch more than 5 million light-years across, containing hundreds of trillions of stars. Compared to these monsters, the Milky Way is a modest spiral, a mid-sized island of starlight floating in a vast cosmic ocean. Galaxy clusters like the Coma Cluster contain thousands of galaxies bound together by immense halos of dark matter, and beyond these lie even larger structures, superclusters where filaments of galaxies weave through space like threads in a cosmic web. Zooming out, the Milky Way sits within the local group. a collection of more than 80 galaxies, including Andromeda and the Triangulum Galaxy. The local group spans about 10 million light-years and is falling toward the Virgo cluster, a massive assembly of thousands of galaxies located 54 million light-years away. This cluster lies within the Virgo supercluster, itself part of an even larger structure known as the Laniakea supercluster, a vast network of galaxies stretching 500 million light-years across. All of this is woven into the cosmic web, a structure that spans the entire observable universe, where filaments of galaxies surround enormous empty voids hundreds of millions of light-years wide. Against this vast backdrop, our place may seem impossibly small. Yet the same hydrogen that fills interstellar space flows through every cell in our bodies. The calcium in our bones was forged in ancient stars. The iron in our blood was born in supernova explosions. The oxygen we breathe was created in the nuclear furnaces of long-dead giants. The universe is not separate from us. We are made from its remnants, shaped by its history, and capable, uniquely as far as we know, of understanding its story. As we look back at the long journey from our quiet solar system to the violent center of the Milky Way, and finally to the edge of the cosmic web, one truth remains. We live in a universe where matter has arranged itself into the ability to ask questions about its own origin. On a small planet orbiting a single star, life has emerged that can trace the structure of galaxies, measure the motion of clusters, and contemplate the fate of the cosmos. The story of the Milky Way is the story of everything that made us. And as long as we continue to explore it, the universe will never be silent. It will keep speaking through the stars, waiting for us to listen.